The cabin looked wrong from every angle. That's what every miner in the Colorado mountains said when they saw what Andreas Brunner was building. The structure wasn't square or rectangular like every proper cabin. It was wedge-shaped, with one end much narrower than the other. The walls weren't parallel. The roof didn't have symmetrical slopes. The whole building looked crooked, lopsided, like it had been designed by someone who didn't understand basic carpentry. It looked like a mistake. They said the crooked walls would be structurally weak. They said the asymmetrical roof would leak and accumulate snow unevenly. They said the wedge shape was a waste of interior space. They said a Swiss immigrant who claimed to know mountain building clearly didn't understand American construction. They said he was building the ugliest, most poorly designed cabin in Colorado. They said it would be a laughingstock. They said a lot of things, and none of it was complimentary. Then February of 1883 arrived, and a massive avalanche released from the slope above the mining camp. The wall of snow, estimated at over 100,000 tons, swept down the mountain at speeds exceeding 80 miles per hour. It hit the mining camp like a freight train made of ice and debris. Cabins built square and solid were smashed to pieces, their walls offering no resistance to the overwhelming force. Men died in structures that had seemed strong and safe. The avalanche destroyed everything in its path, everything except Andreas's crooked cabin. The wedge-shaped structure, with its narrow end pointed upslope toward the avalanche starting zone, split the avalanche flow like a ship's bow splits water. The snow divided around the cabin, flowing on either side, reforming beyond it and continuing down the valley. The cabin shuddered under the impact but held firm. Inside, Andreas felt the building shake and heard the roar of snow passing around him, but he was safe. When the avalanche stopped and the survivors emerged, Andreas's crooked cabin stood intact, while every conventional cabin in the direct path had been obliterated. Suddenly, the ugly, poorly designed cabin didn't look so stupid anymore. The story begins in the fall of 1882, when Andreas Brunner arrived in the Colorado Rockies to work in the silver mines. He was 45 years old, from the Swiss Alps near Zermatt, where he'd spent his entire life in mountains far steeper and more avalanche-prone than anything in Colorado. He'd witnessed dozens of avalanches. He'd helped recover bodies. He'd learned through bitter experience what happened when buildings were positioned or designed incorrectly in avalanche terrain. He understood that in steep mountain valleys, cabin design wasn't just about shelter. It was about survival. When Andreas examined the mining camp where he'd be working, he was immediately alarmed. The camp was built in a narrow valley with steep slopes rising directly above the cabins. The cabins themselves were conventional rectangular structures, built with walls perpendicular to the valley and roofs with equal-pitched gables. To anyone with basic building knowledge, they looked proper and well constructed. To Andreas, with his alpine experience, they looked like targets waiting to be hit. Those conventional designs presented maximum profile to avalanche flows. They were obstacles that would be hit with full force and maximum impact area. He tried to explain this to the mine superintendent, a man named Robert Hayes, who'd been in Colorado mining for 10 years and considered himself knowledgeable about mountain construction. Hayes looked at Andreas's rough sketches of a wedge-shaped cabin and shook his head in disbelief. "You want to build a cabin shaped like an arrowhead? With one end narrow and one end wide? That's the strangest design I've ever seen." "Why would you waste interior space like that?" Andreas explained. "In Switzerland, we have learned that cabin shape matters in avalanche terrain. If avalanche comes, it hits the building with enormous force. A square building, it presents large flat wall to avalanche. This wall must resist full impact. It usually fails. But wedge-shaped building, narrow end facing upslope, the avalanche hits small surface and splits around the building, like water splits around ship bow, much less force on structure." Hayes wasn't convinced. "That might work in Switzerland, but we don't have avalanches here like you're describing. We get snow slides occasionally, but nothing that would destroy a cabin. You're overcomplicating things. Just build a normal cabin. It'll be fine." Andreas shook his head. "You have not seen big avalanche yet." "But you will." These slopes above camp, they are perfect avalanche terrain. Steep, smooth, no trees, faces right direction. When conditions are right, large avalanche will release. Your square cabins will not survive. Hayes laughed. I've been here 10 years. The worst we've had is some snow sliding off roofs. You're worrying about something that isn't a real risk here. Andreas knew he wouldn't convince Hayes with words. He'd build his cabin his way and let results speak for themselves. He selected a building site carefully. Unlike his fellow miners who chose flat, convenient locations, Andreas picked a spot with a large boulder upslope. The boulder would split any avalanche flow before it reached his cabin, reducing the force his building would face. He oriented his cabin with the narrow end pointed directly at the boulder and upslope toward the avalanche starting zone. The wide end faced downslope and across the valley. Construction began in October of 1882. Andreas's design was unconventional in every respect. The cabin was 24 feet long. The upslope end, the narrow end, was only 8 feet wide. The downslope end, the wide end, was 16 feet wide. This created a wedge shape, with walls that weren't parallel but angled to create the taper. The roof was equally unusual. Instead of a symmetrical gable with equal slopes on each side, Andreas built an asymmetrical roof. The upslope side had a steep pitch, approximately 60 degrees from horizontal. The downslope side had a gentler pitch, approximately 30 degrees. This meant the roof peak wasn't centered, but offset toward the upslope side. The steep upslope face would present a sloped surface to avalanche impacts, deflecting snow upward and over the building. The gentler downslope face would shed snow normally, but wouldn't face avalanche forces. When neighbors and fellow miners saw this construction, the mockery was immediate and harsh. Robert Hayes brought other miners to see what he called the most ridiculous cabin design he'd ever encountered. Look at this. It's shaped like a wedge. The walls aren't even parallel. The roof is crooked, steeper on one side than the other. This isn't a cabin. This is a mess. One of the miners examining the structure said it looked like Andreas had started building a normal cabin, made mistakes, and tried to fix them badly. Another said the crooked roof would leak for sure because it wasn't balanced properly. A third said the whole thing looked like it would fall over sideways because the weight distribution was all wrong. Andreas ignored the comments and continued working. The structural elements were actually carefully engineered. The wedge shape meant the upslope wall was load-bearing for the steep roof section, while the downslope wall carried the gentler roof section. The floor joists ran perpendicular to the long axis, maintaining structural integrity despite the unconventional shape. The foundation was reinforced on the upslope side where avalanche forces would be greatest. Every element had a specific purpose related to avalanche resistance. The exterior walls on the upslope narrow end were built extra thick, using 10-inch logs instead of the standard 6 to 8 inches. This provided additional strength to resist impact forces. The walls were also cross-braced internally with diagonal supports, creating a rigid structure that could absorb and distribute impact loads. The steep upslope roof section was built with heavy timbers and covered with overlapping split shingles laid at angles that would deflect snow flow upward. Andreas was essentially building a snow deflector, not just a roof. By November, the basic structure was complete. It looked bizarre, crooked, poorly proportioned. The narrow end seemed too narrow. The wide end seemed too wide. The roof looked lopsided. The whole building appeared to be a carpentry disaster. Hayes visited regularly, each time shaking his head at the strange construction. I've built a lot of cabins in my time. I've never seen anything like this. It's like you don't understand that buildings should be symmetrical and square. This thing looks like it's about to tip over. Andreas remained patient. In Switzerland we have saying, pretty building is not same as strong building. This cabin is built for function, not for appearance. Function is to survive avalanche. Appearance does not matter. Hayes gestured at the steep, crooked roof. That roof is going to accumulate snow unevenly. The steep side will shed snow onto the gentle side. You're going to have a massive snow load on one side and nothing on the other. The whole thing will collapse from unbalanced weight. Andreas had considered this. The steep side sheds snow quickly, yes, but this snow falls to ground, not onto other roof. The gentle side accumulates normally and is built to carry load. The asymmetry is intentional. It is feature, not flaw. The mockery continued through November and December as Andreas completed the interior work. Fellow miners had started calling it the crooked cabin or sometimes the wedge cabin. Andreas didn't mind the names. He'd built exactly what he intended to build. By January of 1883, the cabin was finished, and Andreas had moved in. It was certainly unconventional. The interior space was oddly proportioned, narrow at one end and wide at the other, but it was functional, weathertight, and structurally sound. Andreas was satisfied. January brought heavy snows to the Colorado mountains. Storm after storm dumped snow on the peaks. The snowpack on the steep slopes above the mining camp grew deeper and more unstable. Some of the older miners, those who'd been in the mountains for 15 or 20 years, started to worry. The snow conditions were building towards something dangerous. Small avalanches occurred, loose snow sloughs that ran short distances and stopped. But the big slopes, the steep faces directly above the camp, remained loaded and unstable. Andreas watched the snowpack carefully. He'd learned in Switzerland to read snow conditions, to recognize when slopes were near release. He saw the danger signs: recent heavy loading, warming temperatures creating weak layers, wind loading on lee slopes, lack of anchoring vegetation. The conditions were primed for a major release. On February 9th, 1883, Andreas woke to concerning signs. The temperature had risen overnight. He could hear muffled crumping sounds from the slopes, indicating settling and adjustment in the snowpack. The wind had shifted, now blowing from an unusual direction that would load the suspect slopes even more. He mentioned his concerns to other miners that morning. "We should be prepared for avalanche. Conditions are very dangerous today. Maybe we should not work upper claims today. Stay near camp where we can reach shelter quickly." Most miners dismissed his warnings. Hayes was particularly skeptical. "We've had heavy snow before. These slopes don't avalanche. You're being paranoid." Andreas shrugged. "I hope I'm wrong, but I will stay near my cabin today, just to be safe." At 11:45 that morning, with a crack that sounded like thunder, the slope released. A fracture line over half a mile wide broke across the mountain face. An estimated 100,000 to 150,000 tons of snow began moving downslope. Within seconds, the avalanche was traveling at over 80 miles per hour, a churning mass of snow, ice, rocks, and shattered trees. The miners in the upper claims heard the roar and started running. Most didn't make it. The avalanche was too fast, the distance too great. They were caught and buried, killed by impact trauma or suffocation. In the camp below, miners had perhaps 30 seconds of warning. The roar of the avalanche was deafening. Some men ran for what they thought was safety. Some froze in terror. Some dove into their cabins and hoped the structures would protect them. Andreas, hearing the avalanche start, immediately went inside his wedge cabin and braced himself in the narrow upslope end, the strongest part of the structure. The avalanche hit the camp with catastrophic force. The first structure in the path was a conventional rectangular cabin belonging to a miner named Jack Morrison. The avalanche hit the broadside wall with full force. The wall exploded inward. The entire cabin disintegrated in seconds, reduced to splinters, and buried under 20 feet of snow. Morrison, inside, died instantly. 2 more conventional cabins were completely destroyed, their occupants killed. A 4th cabin was struck a glancing blow, partially destroyed but not completely buried. The miner inside survived with serious injuries. The avalanche was approximately 200 feet wide at its core, with debris spreading wider as it flowed. Andreas's cabin was in the path, but offset slightly from the center. The large boulder he'd positioned his cabin near took the initial impact, splitting the flow. The divided avalanche approached Andreas's wedge cabin from slightly different angles. The narrow upslope end of the cabin, pointed directly at the oncoming snow, presented minimal profile. The steep roof section deflected the flow upward and over the structure. The reinforced walls absorbed the impact without failing. Andreas, inside, felt the building shudder violently. The roar was overwhelming. The cabin shifted slightly on its foundation but held firm. Snow piled against the walls, rising up the steep roof section, but the flow divided and passed around the wedge shape. Within 30 seconds, the main avalanche had passed. Andreas's cabin was partially buried, with snow piled against the upslope narrow end to a depth of about 8 feet. But the structure was intact. The walls had held. The roof hadn't collapsed. Andreas was alive and unhurt. Outside, the scene was devastation. 3 cabins were completely gone, buried under massive debris piles. One was partially destroyed. 2 miners who'd been caught in the open were buried. The camp, which moments before had been a functioning mining operation with a dozen structures and 20 men, was now a disaster zone. As survivors emerged and began rescue efforts, they saw Andreas's crooked cabin still standing, partially buried but clearly intact. Hayes, who'd survived by being in a cabin at the edge of the avalanche path, stared at Andreas's wedge-shaped structure in disbelief. "Your cabin survived. How is that possible? Cabins closer to the edge were destroyed. Yours was in the direct path. How is it still standing?" Andreas emerged from his cabin and surveyed the damage. The avalanche flow had split around his wedge shape exactly as he'd designed it to. The narrow end had presented minimal resistance. The steep roof had deflected snow over the structure. The reinforced construction had absorbed the forces. "It worked as designed," Andreas said simply. "The wedge shape splits the flow, like ship bow splits water." The avalanche went around, not through. Hayes looked at the destroyed cabins, then back at Andreas's intact structure. "I called your design ridiculous. I said it was crooked and poorly built." "I was wrong. Your cabin is the only one that survived a direct hit. That's not luck. That's engineering." The rescue efforts that followed were grim. 3 miners were found dead in the debris of their destroyed cabins. 2 caught in the open were also found dead. 1 seriously injured miner was pulled from the partially destroyed cabin and would eventually recover. 7 deaths total, with several more injured. It was the worst disaster in the camp's history. In the weeks following the avalanche, as the camp recovered and assessed damage, Andreas's cabin became a subject of intense interest. How had the crooked design saved his life? What principles had he applied? Could others build similarly? Andreas explained patiently to anyone who asked. "In avalanche terrain, building shape matters. You must minimize the profile facing upslope. You must design to split or deflect flow, not resist it directly. You must reinforce where forces will be greatest. This is not new knowledge. In Swiss Alps, we have built this way for centuries. But here, people did not believe avalanche risk was real." If you're fascinated by how Andreas's counterintuitive design based on Swiss alpine knowledge saved his life while conventional cabins were destroyed, and you want to hear more stories about expertise that defied common sense but proved correct under extreme testing, make sure to hit that subscribe button. There are so many more incredible tales of specialized knowledge waiting to be discovered. 3 miners rebuilt their cabins that spring using principles Andreas shared. They built wedge shapes, narrow end upslope, steep roof sections facing the avalanche zone. They reinforced structural elements on the impact side. They positioned their buildings to take advantage of terrain features that would split flows. None of these new cabins were exact copies of Andreas's design. Each adapted the principles to specific site conditions and avalanche directions, but all followed the core concept: present minimal profile, deflect rather than resist, build for the forces you'll face. The science behind avalanche-resistant building design is based on understanding avalanche dynamics and structural engineering. Avalanches exert enormous impact forces, measured in tons per square meter. These forces increase with the square of velocity. An avalanche traveling at 80 miles per hour exerts roughly 16 times the force of one traveling at 20 miles per hour. Impact force also depends on the area presented to the flow. A wall 10 feet wide presents 10 times more area than a wall 1 foot wide, and therefore receives 10 times more total force. Andreas's wedge design minimized the area facing the avalanche. The narrow upslope end was only 8 feet wide instead of the 16 feet wide that a conventional cabin would present. This halved the total force the structure had to resist. The wedge shape created flow separation, the same principle that allows ship bows to part water. When fluid or granular flow hits a wedge, it splits and flows around the obstacle. Some energy is lost to turbulence at the split point, but most of the flow passes around rather than impacting the full width of the obstacle. This dramatically reduces force on the structure. The steep upslope roof section created a deflection surface. Avalanche snow hitting the steep slope was redirected upward and over the building rather than impacting horizontally. This is similar to how airplane wings redirect airflow. The redirection changes the force vector from primarily horizontal to partially vertical, reducing the structural loading. The asymmetric roof design also prevented problematic snow accumulation. A symmetrical roof in avalanche terrain can catch avalanche debris on the downslope side, creating massive localized loads that cause collapse. Andreas's steep upslope face ensured debris couldn't accumulate there, while the gentler downslope face was protected from avalanche impact. The reinforced construction on the impact side recognized that forces wouldn't be uniform. The upslope narrow end faced maximum forces and was built strongest. The downslope wide end faced minimal avalanche force and could be built lighter. This efficient distribution of strength where needed reduced overall construction cost while maximizing safety. Modern avalanche engineering has validated all of Andreas's principles. Contemporary avalanche-resistant structures use wedge or streamlined shapes to minimize impact forces. They incorporate deflection surfaces on the upslope side. They reinforce structural elements facing the hazard. They position buildings to utilize terrain features for protection. Andreas was applying in 1882 what wouldn't be formalized as avalanche engineering until the mid-20th century. His knowledge came from centuries of alpine building experience, accumulated through tragedy and hard-won lessons. The contrast between Andreas's cabin and the conventional cabins during the February 1883 avalanche demonstrates the importance of design for specific hazards. Conventional cabins were well built for general mountain conditions. They were square, sturdy, properly constructed, but they weren't designed for avalanche impact. When that impact came, they failed catastrophically. Andreas's cabin looked poorly designed for general purposes. It was crooked, asymmetrical, odd-looking, but it was perfectly designed for avalanche survival. When the avalanche came, it performed exactly as intended. Over the following years, Andreas's wedge cabin stood as proof that unconventional design could be superior for specific conditions. Miners and mountaineers visiting the camp would examine the structure, trying to understand how it had survived when others hadn't. The story spread throughout Colorado mining districts. The Swiss miner's crooked cabin that split an avalanche and saved his life. Some listeners built wedge-shaped structures in avalanche terrain. Others incorporated elements like steep upslope roof sections or reinforced impact-facing walls. The knowledge was spreading, slowly, through the network of mountain workers. Andreas himself continued mining until 1896, when at age 59 he retired and returned to Switzerland. His wedge cabin was occupied by various miners over the following years, all of whom appreciated its proven avalanche resistance. The structure stood until 1922, when the mine finally closed and the camp was abandoned. The cabin deteriorated over subsequent decades and eventually collapsed, but its location remained identifiable by locals for many years after. Modern avalanche researchers studying the area have confirmed that Andreas's cabin site was indeed in a high-risk zone. Computer modeling shows avalanche flows in that valley would have impacted his location with significant force. The wedge design and positioning relative to the protective boulder were essential to survival. The cabins destroyed in 1883 were in similar or even lower-risk locations, but their conventional designs made them vulnerable. The psychological challenge of building ugly structures is real. Andreas's cabin looked wrong to everyone who saw it. The crooked walls and asymmetrical roof violated every aesthetic norm of building design. People couldn't accept that something so visually displeasing could be functionally superior. This aesthetic bias caused miners to reject Andreas's design advice initially. They'd rather have a pretty cabin that might kill them than an ugly cabin that would save them. Only after the avalanche proved the ugly design's worth did people overcome aesthetic objections. The lesson about form following function is important. Andreas's cabin was ugly because beauty wasn't the design criterion. Survival was the criterion. Every design decision was made to optimize avalanche resistance with no consideration for appearance. The result was a crooked, asymmetrical structure that looked like a mistake but functioned perfectly. Modern architecture often sacrifices function for form. Buildings are designed to look good, with structural and functional considerations secondary. Andreas's approach was the opposite. Function determined every aspect of design. Form was irrelevant. Before we conclude this remarkable story of how alpine engineering knowledge saved a life when common sense construction failed, if you've been captivated by how Andreas's expertise allowed him to see hazards others missed and design solutions others rejected, and you want to discover more forgotten innovations that defied convention but proved correct, take a moment to hit that subscribe button. The most incredible stories of frontier expertise are still to come. The economic value of Andreas's design was proven dramatically. He invested perhaps an extra week of labor in the unconventional design, calculating angles, reinforcing specific areas, ensuring proper orientation. This investment saved his life and his entire winter's supplies and possessions. Miners who lost their cabins lost everything and had to rebuild from nothing. Andreas lost nothing. The return on investment was infinite. The social dynamics after the avalanche were telling. Before the disaster, Andreas was mocked for his crooked cabin. After the disaster, he was recognized as an expert whose knowledge had value. The knowledge hadn't changed. Only the willingness to acknowledge it had changed. This pattern appears throughout history. Experts are dismissed until disaster validates them. Then they're celebrated. But the expertise was always real. Andreas's generosity in sharing his knowledge after the avalanche was crucial to its spread. He could have kept his techniques proprietary, perhaps charging for consulting. Instead, he taught freely, helping miners understand the principles and apply them to their own situations. This collaborative approach saved lives and spread valuable knowledge. The practical applications of avalanche-resistant design remain relevant. Anyone building in avalanche terrain should consider building shape, orientation relative to hazard, deflection surfaces, and reinforcement strategies. These principles, which Andreas demonstrated, can prevent tragedies. Modern technology has enhanced avalanche hazard assessment with computer modeling, snow science, and monitoring systems. But the fundamental design principles Andreas applied remain valid. A wedge-shaped building minimizes impact forces. Deflection surfaces redirect flows. Strategic positioning utilizes terrain protection. These truths are timeless. The validation period for Andreas's design was immediate and dramatic. One avalanche proved the design worked. Unlike innovations requiring years of testing, avalanche resistance is proven quickly and definitively. Structures either survive or don't. Andreas's survived. Conventional structures didn't. The comparison between Andreas's cabin and destroyed cabins tells everything. Andreas, crooked design, looked wrong, engineered for avalanche, survived direct impact. Morrison and others, conventional design, looked right, built for general use, destroyed by avalanche. Appearance was opposite to performance. Understanding hazards was essential. Conventional wisdom was deadly. The crooked cabin that everyone mocked wasn't crooked. It was angular, purposeful, optimized for a specific threat. The conventional cabins that looked proper weren't safe. They were vulnerable, inadequate for the actual hazard they faced. Andreas knew this from the start. Everyone else learned it when the avalanche came. The story of Andreas Brunner and his wedge-shaped cabin is ultimately about the value of specialized knowledge, the courage to build differently despite mockery, and the vindication that comes not from argument but from survival when others perish. It's about a Swiss miner who understood avalanche dynamics better than anyone in Colorado, who designed a cabin that looked ridiculous but was actually perfect, who saved his own life while conventional designs failed catastrophically. The cabin looked crooked. The walls weren't parallel. The roof was asymmetrical. Every aspect seemed wrong to people with conventional building knowledge, but every aspect was right for avalanche survival. The narrow upslope end minimized impact area. The steep roof deflected snow flow. The wedge shape split the avalanche. The reinforced construction absorbed the forces. Everyone said the design was ridiculous. Everyone said Andreas didn't understand building. Everyone said the crooked cabin would fail. They were wrong about everything. The crooked cabin survived the avalanche. It split a 100,000-ton flow of snow, traveling at 80 miles per hour. It protected its occupant while conventional cabins were obliterated. It proved that engineering for specific hazards trumps conventional design every time. The mockery stopped when the avalanche debris cleared and Andreas's cabin stood intact. The learning began when survivors asked how the crooked design had saved him. The respect came when people understood that ugliness didn't mean poor design. It meant different design, optimized design, life-saving design. That's how expertise gets recognized. Through extreme testing, through survival when others die, through results so dramatic that even skeptics must acknowledge truth. Andreas's cabin provided those results. His design worked when tested by nature's violence. His knowledge proved superior to conventional wisdom. The crooked cabin survived the avalanche. In surviving, it proved everything. Knowledge beats aesthetics. Function beats form. Understanding hazards beats following tradition. Andreas understood. His neighbors didn't. The avalanche sorted out who was right. The man with the crooked cabin was right. The men with proper cabins were wrong. That's the story. That's the lesson. And that's why Andreas Brunner's wedge-shaped design deserves to be remembered. He built it crooked when everyone said build it square. The avalanche proved who was right. The crooked cabin survived. And in surviving, it vindicated every principle Andreas had tried to explain.